Electricity. Now, when starting electricity, it's always good to ask your students, hey, what things in your house use electricity? And so we got toasters. I always get the students to put their hands up before they say something, otherwise you just get a load of people shouting out. And that encourages people to shout out. One of the things I say to my students is that I'm a little deaf and that I have to partly lip read. It's stretching the truth a bit. But it does mean that my students don't shout at me, because I ignore them if they shout at me. I'm only polite to them out on toasters, washing machines. So they put their hands up to get things on the board or to get my attention. And if they just shout out, then I don't say anything to them. I don't reply. I don't even notice they exist. And they soon get the message. Washing machine, cookers. Oh, of course, some cookers are gas in some people's houses. Toasters. Right, now, then I'm saying to them things, I'm particularly interested in ones that you can pick up and look all around, like you can toasters. You can look underneath the toasters and say what it says. And so we've got kettles. We've also got laptops. Right, now laptops are going to be different because the toasters and the kettles you plug in to the main electricity in your house. See what I did there? The main mains. And it's called the mains, is the main electricity in your house. So with the laptops, you've also got them plugged in sockets. Well, there are all the sockets, but there's extension leads. Extension leads. And so I give them this task just before we finish the lesson, just before starting electricity, because I want them to say to me what they say on them. With washing machines and cookers and toast and other big items, fridges, they are plugged into the mains, but you can't pick them up and see the little metal label on them that tells you how many V for V's there are, and how many Z's there are, and how many R's there are. So these are important ones. When I'm teaching in Hong Kong, I also said the air conditioners, AC. Because the AC, you can often see the label that tells you how many H's and there are. And then I say to the students, well, what are these words? And sometimes the students already know. So let's assume one person knows. Volts. And maybe they'll know amps. And so I say to them, oh, what do the volts do? What's the difference between the volts and the amps? Do they know? And most students won't know good. So their homework is to go home and look at the kettles, laptops, extension leads, and etc. and see if they can get information on you. And so you're going to get a lot of 220 volts. In America, we talk about this. So if you've got something from America, it's 120 volts. You will see 230 volts, and you'll also see 240 volts. And so, we'll talk about this. Obviously, the amount of volts doesn't seem to matter that much. Some people's toasters say 220. Some people's toasters say 240. So, okay. But in America, they say 120 or 110 volts on all the equipment. So if you buy something in America and bring it to England, Europe, or Hong Kong, and you plug it in, expect to lose it unless you've got some kind of transformer. So we're writing all these things on the board and on this piece of paper. Before we even start the subject, I want to make the subject real for the students, so they're looking around the house, finding things. Oh, of course, there's the TV. The TV is also on the mains. And you might be able to see behind the TV also says somewhere between 200 volts and 250 volts. Okay, and then we've got the students that looked at other things, their laptops. Their laptops might say 15 volts. And then we get to, why do we put V rather than volts? Oh, because it's just quicker. and it takes up less room, and V for volts. But you also might see on your battery cells it says 1.5 volts. Hold on, this is a big difference. And on the laptop it says 15 or 12 or 10, depending on the make of the laptop. So what's it to do with? So, hold on. Sorry about that, a bit of noise. So the cells are in you're possibly in torches, but most people don't have torches nowadays. But your cells are in small items like the remote control for your TV or other remote controls. And so what's meaning that you need huge volts here and small volts here and tiny volts there? What's going on? And hopefully after a few suggestions from the students, colour, green, white things need high volts, that's not it. It will get size, because 1.5 volts is enough to push the electrons around, like 10 centimetres to 15 centimetres. Of course, quite a lot of remotes have two 1.5 volts, and so we'll talk about that. They are helping one another out, and they give you 3 volts. Okay, and so bigger systems, like a laptop, if it's 10 times bigger, it needs 10 times the amount of volts. So why are toasters? Toasters aren't 10 times bigger than laptops. No, this is to push the electricity around the whole house, the mains electricity going through the walls of your house. Yes, do not drill holes in the wall of your house, because you'll end up giving yourself electric shock, and the electricity will turn off in that area, and you maybe get a big bill from an electrician, and maybe you'll have to have the wall all dug out in order to fix it. But you might die. So these are the small lessons that we try to put in along the way with electricity. But we're pushing on this. This is the push. To get the distance is the volts. Okay, sorted. They all said 50 hertz. Well, the kettle, everything plugged into the main says 50 hertz. What's hertz? We'll get to that later. So, next one, we want to do amps. And we'll hopefully get the big things that need lots of electricity, need lots of amps. Lots of electricity, electrical power equals lots of amps. Okay. So now we've got the word power, and we're going to start getting our first equation. Power equals amps. Because physics equations aren't just there for you to remember. They mean things. There's logic to them. If you double the power, you need to double the amps. But of course, it's an equation, so it's going to be more than just amps. What are we going to do with the volts? So, to get power, are we going to divide by volts? So that means that these things plugged into the mains will have a very low power because they've got high volts. Whereas your remote control uses lots and lots of electricity per second. Per second. The amount of electricity, it's electricity per second, so electricity energy is in joules per second. So that's energy per second, electrical energy. Okay, and so it's a bit of a messy whiteboard we're slowly building up, but we're making a story and we're bringing all the students along in the story at the time. So hopefully we'll get someone to say it's times by volts. Not remembering, but just realizing that the machines that take lots and lots of electrical energy, toasters, washing machine, kettles, things that really take loads of heating up, and they have lots of volts. And also lots of amps, because we've also got the amps from a toaster. I don't know, amp toaster. Let's call it A amps. Maybe that's a bit big. Oh, I've written it off the board. Got it. Anyway, so that's why we've got this equation. Hold on. I'm not sure why that's going off. Cool. So that's our first equation. It makes sense. We're moving on. Right, the next one I want to do is stopping electricity move. Why would we want to stop the electricity move? Because we want the electricity to move really quickly through some things and then slowly through others. And where's they're moving hard, they're giving off lots of heat. So as they go through a rectangle, they give off lots of heat. As they go through a wire, this is a copper wire. Well, wires are just drawn as straight lines. And okay, so this is obviously my toaster. Giving off lots of heat. This diagram will also do for my kettle. It's the same diagram in physics. Anything that gives off heat, it's just a wiry, and a rectangle which is going to resist the movement of electrons. That's why it's called a resistor. Okay, so what does resist mean? Oh, it means, it's going to make it difficult for the electrons to go through. I asked the class, what does resist mean? Resisting arrest being a good example. You're fighting against the police, you don't want them to arrest you, you're going to get in even more trouble if you punch that policeman, don't it? Okay, so up here, can we use a cell to power a toaster? No. Cells only give 1.5 volts. That's just not enough volts for a toaster. No. Okay, so what we're going to do is draw two little circles and a wavy line. Okay, what's that? Well, the wavy line says the electricity starts going in one direction and then afterwards it's going in another direction. It's like a wave. It alternates between going towards the power station and then away from the power station. All right, what's a power station? So a power station, hopefully we're going to get the students saying that's a big factory that makes power. It's a power station. So how do power stations work? What do they use? What energy do they use? And hopefully we'll get coal-burning power stations eventually, after everybody says, oh, there's solar power and wind power and all the other ones, wave power, hydroelectricity. The one that mostly, in the early part of the 21st century, is giving most of the electricity to your house is coal-burning power stations, and that's why leaving the lights on in your house means that they're burning more coal to make you the electricity that you're taking out of the system. They're putting the electricity back in, and don't do this because burning coal gives CO2, and that's global warming and all that. Right, where were we? Oh yes, the wavy line. So this is mains electricity. It goes one way and then the other way. And then we talk about a rock band from Australia. Name a heavy rock band from Australia. Okay, this might take some time, but eventually, hopefully, we've got somebody who says AC/DC. Okay, because this one is AC and DC is this one. Okay, now we need to know what's the C in AC/DC. SE equals. Okay, and it's going one way, then another way. What's a word for one for you, one for me, one for you, one for me, going left, going right, going up, going down, alternating. Hopefully we'll get that alternating. And this one is going in one, it's going one way only. And therefore we're going to get direct. So here we go. DC equals direct current. Oh, Don't worry. Sometimes I have to. Sometimes, when the students aren't getting a word that I want, I'll say that the word starts with k and ends in "aren't." Yeah, so sometimes you have to push the lesson along. This is alternating current because it's AC. Why current? Well, because it was thought to be like water, the current of a water going down a river. So, this is a river going in one direction, which is the kind of river you're used to in, well, rivers. This is a river that alternates, yes, because sometimes some rivers, like the start of the Thames River, big rivers, the Amazon River, the river actually changes direction near the river mouth when it's high tide. The high tide pushes salt water up the river. That's why you get saltwater marshes around the Thames. That's where I grew up. Yeah, it's not very nice. It's a bit yucky around saltwater, to be quite honest. Saltwater marshes, not so pretty, not many flowers. Anyway, so sometimes the current goes backwards and forwards. It alternates high tide to low tide, but mostly rivers go downhill. But they do go uphill, kind of uphill. They go in when the tide is high. Cool, so we've got AC and DC. We've got power equation. Oh yes, now I need to link resistance into an equation. Right, so if you've got lots and lots of resistance, hold on, and at this point I'd say to the students, well, I remember it as V equals IR, but I'm going to teach it you in the V over I format. Okay? I remember it as V equals IR, it's just in my head that way. That was the days when you had to remember all these formulas. Power equals amps times volts, joules per second, energy over time. Hold on, let's get back to this one. Joules is energy over time equals power. Powerful machines, big, powerful robots use a little bit of energy or a lot of energy. They're big, powerful diggers use lots and lots of energy. Usually it's a diesel engine. And they do the digging a hole to digging a swimming pool in a big amount of time or a short amount of time? Well, in a short amount of time compared to this other digger. So big diggers with big, okay, good drawing. Big diggers. There's a guy smiling. Big diggers use lots of, and there's a small digger. Okay. Okay, small digger. Same size guy. Oh, a tracked vehicle, really, isn't it? Big diggers use lots of energy in the case of like petrol or diesel, but they dig the swimming pool in a short amount of time. Small diggers use small amounts of energy and take lots of time. This one gets lots of power because it's big divided by small. Big numbers divided by very small numbers gives you double big numbers. This is powerful. Power equals energy divided by time. This one, not so powerful because it takes a large amount of time and it uses a small amount of energy. Small number divided by a big number gives you a very small number. So we'll illustrate that by doing a couple. Let's do 100 joules divided by 1 second. No, 0.1 seconds. Okay, it's unfeasibly small for a digger to take that amount of time. But anyway, we end up with 1,000 power is in. Aha, now we have to get the units. We don't want to keep saying joules per second here. So then I give them the fabulous sentence of what's the unit for energy? There we go. The unit for energy, power. Oops. And this because the guy with the powerful machines, when industry was first starting, was a Mr. Watt. He didn't invent the steam engine. You will get that on YouTube a lot. But he sort of perfected it. It was Newton that came up with not Newton. It was a new guy. And then Watts came along and changed it and made it really good. And that's why he got the name for power. How powerful. That's obviously a powerful digger. Takes lots of energy and a very small amount of time. Whereas if this one is, that's 0.5 joules and divided by 50 seconds. Okay, come on, let's make this not seconds, let's make it, oh no, then it would, if I have to give it in seconds, otherwise it wouldn't be watts. If I go and turn that to hours, I haven't got watts anymore, it has to be in seconds. Okay, so 0.5 divided by 50, hold on, 0.5, 50, 55, 0.1 divided by 10, 0.01 watts. The power measured in watts, exactly. And so this is how we get the first few equations going. Hold on, I haven't done resistance, so here we go. So maybe this is a couple of lessons going. As we get one equation like power equals amps times volts, then we'll get the students to make a few questions like this with their own numbers from their homes, finding out what power it is. And I mean, some of these machines actually might say a power amount, and then hopefully the amps times the volts will equal the power. Fingers crossed, because it's sometimes just not that easy. Okay, and this one here, last one I'm going to do today. Right, okay, so if you've got something with lots and lots of resistance, it's really hard to get through, it's a very thin wire, you need lots of volts to push the electrons through. Lots of push. Remember, volts was push. And you're going to get a very small amount of electricity, very small current. Very, very few electrons are actually going to get pushed through a thin wire. Let's draw a thin wire compared to fat wire. Okay, and so lots and lots of electrons can get through here. It's hard for electrons to get through here, and that also works for roads. So if you've got a very thin, difficult road, and that's a car going through, whether it's a car or an electron, the actual wire's width really matters. Hold on. Oh, yeah, no, that's good, because now I've got... No, I haven't got electrons going... No. See, I was thinking cars going the opposite way, but no. Circuits are one-way systems. Even when you're alternating, everybody is going to the right, and then the AC current, 1/50 of a second is going to the left, and that brings in why Hertz was 50. It's the amount of times per second that the alternating current goes the opposite way. All things across the world. Don't think there's anywhere that's got any exception yet, because they all use 50 Hertz. Everywhere. Good. And there's your start to GCSE electricity and a revision for GCSE to help you toward your A-levels. Cool! Hope that helps, and hope it helps the teachers in the way to teach it too. Bye!